These equations are the mathematical foundations of classical physics. In Coulomb's law, Poisson's gravity equation, or Kaluza-Klein unification, the same constant appears, 4 pi. In traditional physics, 4 pi represents the continuous geometry of a perfect sphere, defining the measure of its total surface area. This reliance on smooth, continuous space is rooted in the history of physical measurement. Classical experiments and the instruments designed to conduct them were built on the assumption that space itself was an unbroken medium. Because of this, classical physics views the fundamental constants of our universe almost entirely through the lens of smooth spatial fields. The ODT-BT framework shatters that assumption. It abandons the idea of smooth spheres and replaces them with a sharp, discrete geometric substrate. This substrate is built on the icosahedron. Vertex subtends a precise solid angle of pi/3 radians, or 60 degrees, known as the theta 60 concept. When you multiply those 12 vertices by the pi/3 angle, the result is exactly 4 pi. We are left with a central mystery. Is the appearance of 4 pi in both smooth equations and sharp icosahedral geometry just a coincidence, or is it the signature of a shared physical reality? To find the connection, we have to look at a rule governing the geometry of continuous surfaces, the Gauss-Bonnet theorem. On a closed continuous surface like this sphere, total curvature is always exactly 4 pi. This value is a topological invariant. No matter how much you stretch or distort it, as long as it doesn't tear, the curvature remains locked at 4 pi. In the continuous world, 4 pi functions as an absolute structural limit dictated by the object's topology. The discrete world follows an equivalent mathematical rule with deep historical roots. Descartes' theorem states folding a plane into a vertex leaves an empty wedge, the angular defect, and icosahedron's 12 vertices each have a pi/3 defect. Summing them assembles a complete 4 pi circle. For any sphere-like shape, this total is always exactly the same. The 4 pi found in continuous physics and the 4 pi in the discrete icosahedron are fundamentally the exact same topological object. They are simply two different ways of expressing the same mathematical truth. The framework identifies this connection as position B, a layered articulation of how discrete and continuous systems interact. In this theory, icosahedral geometry is a discrete manifestation of universal topological constraints. It is a mathematical requirement, not an arbitrary choice. This makes ODT-BT a recovered articulation. The framework maps established topological laws to the constants of physics, identifying a shared structure between different geometric languages. From this perspective, the foundational equations of classical physics emerge from a discrete geometric substrate. While this mathematical proof is only one piece of the puzzle, it places the theory's foundation on an unshakable mathematical footing. The next phase of the investigation focuses on how this discrete architecture parallels work in quantum gravity research and the study of quasicrystals. We are finding that the most complex systems in the universe rest on elegant, recovered truths. This has been Field Notes.